So one of the things that I've been doing throughout my years in the industry, I started in actually in protection engineering at a company called Beckwith Electric many years ago, back in the early 90s. And I cut my teeth under a gentleman by the name of Charles Mosina, who was really instrumental in getting me started in protection and control. And he was a generator guru. In fact, he was the chairman of the IEEE Committee on Rotating the Protection of Rotating Machinery and wrote a really wonderful tutorial on that. But after my years at Beckwith and moving to Omicron Electronics, of course, my main focus at that point in the early days with Omicron was protective relaying and testing protective relays. And one of the things that has certainly evolved over the years is the introduction to digital technology with protection systems. And although it may seem to you that digital relays have been around for a very long time, in my world, it's still kind of new and evolving technology, especially with substation upgrades and automation. Digital technology for protective relay systems gives us a lot of great benefits when you compare them to the old electromechanical and static relays, especially when it comes to protecting transformers. And one of the things, of course, that always comes along with new great technology for protective relaying comes along with what comes along with that is increased complexity. And as those of you who do test relays or who actually do settings in relays, you'll know that back in the early days, it was always very simple. We calculated tap settings for the differential. We could test one element at a time because there were single element relays. And now you have all kinds of complexities involved with multifunction relays. So I'm going to use two examples, and these are fairly common in the industry of digital relays for protection of transformers. One is the Schweitzer 787. It could be a 587 or different variations of the Schweitzer transformer relay, but this is a common one. And the other is a Beckwith M-3311, and I chose that one because actually, I want to illustrate some of the differences that you're going to find between different manufacturers for protective relaying. And while the 787 is quite versatile in terms of where it's applied, usually in transmission and distribution power transformers, the 3311 is one that generally gets used with generator step-ups. And that is primarily because you have Beckwith relays on the generator and a Beckwith relay on the GSU, and they kind of work hand in hand in protecting those systems. So we'll go behind the scenes of some automated relay testing and setting functions to make sure that people are really in a good place when it comes to understanding these. So basically for transformer protection, we're going to split this up into three categories. One would be for your internal faults, and this is your phase differential, and then your tank ground over current relays, and these are things that are internal faults to the transformer itself. And then you have then you have what's called your through faults. Okay. And these are faults that occur outside the protective zone of that differential relay internal to the transformer. So if something happens upstream or downstream that may cause damage to the transformer, they're in a group all their own as well. And then other things I call abnormal operating conditions. These are things that happen on the system that can influence or cause harm to the transformer itself. Things like undervoltage, overexcitation, and then some elements that may be there, such as underfrequency for load shedding applications. If we look at a typical one-line diagram, and all digital relays have one-line diagrams to illustrate, where they're connected to the system and, what protective elements are there. I kind of like to look at these in two different groups for transformer protection. One which I'd call proactive and one which is reactive. And it's important to understand which is which because I would consider a differential relay to be reactive. And that is this, that if your differential relay trips at any given point in time, and it's not a false trip or a nuisance trip or something that came from a bad setting, that means that the fault is already present within the transformer, within the protective zone of that protective element. The damage is done. It's just there to make sure that no further damage is done or any catastrophic damage occurs as well. And then I'd look at those that are proactive, and that is what protective elements are in the protective relay system that keep damage from occurring from outside influences, things like overvoltage and things like volts per hertz, and things that would cause potential harm to the transformer, if it weren't taken offline in time. So aside from the electrical elements, electrical protective elements, we have some mechanical ones as well. Things like sudden pressure relays and Buchholz relays, and things again that can sense a problem with the transformer and take it offline before anything happens. And I would say that it's important to understand the difference between the two. Now, the complexity of the digital relays wasn't typically around back in our days, Randolph, as you were referring to, back when a protective element was one relay. For instance, a GE BDD or an ABB HU relay was a single element relay that tripped when it saw an imbalance in the currents between the primary and the secondary sides. Now you've got all these other elements that are built into one device, and we have to make sure that they get configured and tested correctly. Um, if you see a one line, this is a one line diagram. It looks very similar to the Beckwith, and this is from the Schweitzer, where you've got your high side and your low side CTs, where your differential relay is connected to look at any imbalance between both sides of the transformer. And then your other relays here that will protect you from, outside influences. But there's some other functions here that are additional to all your digital relays that are very important as well. Things like breaker failure, a breaker wear monitor, event reports, RTD inputs for thermal monitoring, restricted earth fault, sequence of events, loss of potential, through fault monitoring, and oscillography. Now, let me give you an example why these are important. When I worked at Beckwith Electric, I'd have customers call me up and say, my relay tripped while, overnight, and we'd like to have some assistance from your team to find out what happened, what caused the event, and if we have any potential damage. Well, my very first question was, okay, well, can you send me your sequence of events record and your oscillography that the relay captured? And then it would kind of go quiet for a minute, and then I'd get this, well, we forgot to enable that in the relay. And I'd be like, can't help you. It's not much I can do in terms of help diagnosing the problem. So very, very important. The first thing at hand is to make sure with all these functions here that they get utilized, because each of those components not only can give you some valuable information over the course of time, like a through fault monitor, but also in the event that you do have a problem, that you can easily kind of diagnose that, yeah, you had a bad trip, and there's potential damage that's inside the transformer. Now, I'll give you another example. We had a situation where a gentleman from a field service testing group, a NETA company, came to me, and he said, Drew, he said, I got an interesting call over the weekend. Somebody gave me a call and said that a protective relay had tripped on a GSU at a nuclear facility. And the guy who they called was the one who commissioned the relay. So they called him out immediately. And he goes out to the field, and by the time he gets there, the foreman of the substation group had the transformer completely disconnected, had scaffolding around, and was getting ready to do some thorough testing on the transformer. And so the technician walks up to him and he says, well, by chance, did you look at the oscillography and the event record out of the relay? And being a substation maintenance guy, he was kind of dismissive. He said, "No, Sonny, go away. We got work to do. We got to figure out what's wrong with this transformer." As it turns out, when they looked at the oscillography, there was absolutely no 87 present during the trip. It was a nuisance trip from a faulty processor in the relay itself. So these are important things. The very first thing you always want to do if a relay trips or takes something offline is look at the sequence of events and look at your oscillography to see if a fault really did occur and what it was that could have possibly happened. Now, between the two relays that I'm illustrating today, one of the things that's very important to understand when you do relay settings or if you do relay testing after the settings are present, or even if you're out doing maintenance testing on a transformer, it's very important to understand the transformer connections and how it's connected to the system. And usually, this is of course always ever present on the nameplate of the transformer. Whether you have a delta on the high side and a Y on the secondary side or vice versa, what that phase rotation represents between the primary and the secondary side. For instance, a delta on the primary, Y on the secondary with a 30-degree phase shift could be considered or construed as a YD1, one being an extra 30 degrees. Of course, the primary and secondary sides are always 180 degrees out, but what is considered 30, 60, 90? It's like a clock going around. And because one of the reasons is if you don't have this configured correctly in the relay itself, or you don't test it accordingly, you either won't get a good test of the relay when you're commissioning it, or the relay is going to nuisance trip when it comes online, because if you don't have those phase angles compensated correctly, you're obviously going to get a nuisance trip. Well, what's important to understand here, and I hate to say this, but the one best way to understand the terminology that relay manufacturers use is to read the manual. And I know that's a difficult test. Nobody likes to read manuals, but uh, but that is important because what you'll see here is on this side, on the left-hand side, those are how Schweitzer represents the different configurations. Over here is what you'll find in the Beckwith system for the IEC connection description versus the Beckwith standard connection and Beckwith custom connection. So even though they're representing the exact same configuration, they could be labeled differently. For instance, you've got a YD11, so that's Y primary, D secondary with 11, okay, which would represent 330-degree phase shift between the two windings, which you can also be called YDAB. Okay, so these are things that are important to understand when you go to configure the relay and when you go to test the relay. And this is all present on the nameplate. Okay, the transformer nameplate, the problem with them is they don't always look the same from one manufacturer of transformer to the other. So you have to look at them very carefully. It's going to tell you your voltage ratings. It's going to tell you your CT ratios. It's going to indicate how the transformer is connected, the primary voltages, the secondary voltages. If it's got a on-load tap changer, it's going to tell you exactly what the primary and the secondary voltages are going to be based on the tap position and then how it's connected. So this is critical information, not only for setting the relay, but for testing the relay. So for instance, if you're going to calculate or verify the calculation of the tap settings on the primary and secondary windings, here's the information that you need to know. The MVA rating of the transformer, the high side voltage, the low side voltage, the vector group in terms of how it's connected, okay, the primary and the secondary CT ratios, because that's the information that the relay is going to use to calculate your tap settings between the primary and the secondary side. And we know from experience, even in electromechanical days, those taps are never even, because you have to balance the currents between the primary and secondary windings. That's Kirchhoff's law, right? Current coming in equals current flowing out. And if your tap settings aren't compensating for the different voltages on each side and the different CT ratios, you're going to have a problem. So this is important information. Incidentally, the impedance value that's stamped on the transformer nameplate, that's very important too, but not typically for not necessarily for relay settings, but for when you're doing tests such as leakage reactance on the transformer itself. So when we go to set up the Beckwith system, and the Beckwith, one thing I always liked about the Beckwith relays is the settings are actually quite easy to understand. They're very graphical and they're very kind of easy to understand. And for instance, if you have voltage, what your nominal voltage is, your CT windings, how they're connected, whether they're Y connected or delta connected, your CT ratios for the primary and the secondary side, okay, are all easily settable right in these little setting boxes right here. And then you have a nice graphical display in a vector diagram what that looks like. You know, your phases, your phase rotation, and your amplitudes. Really nice graphics, very easy to set up. Okay, now here's the big difference between the Beckwith and the Schweitzer. When you have a Beckwith relay, and you're putting your slope settings in, slope one, slope two, slope intercept, you have to, and this is very important, calculate by hand what the tap settings would be. For instance, if you put in your CT ratio settings in some relays, along with the high and the low side voltage and how it's connected, it's going to calculate the tap settings for you. The Beckwith does not. And I kind of like this. I know it sounds like, oh, I got a bunch of math to do when I'm setting the relay or testing the relay, but I think that's in some cases is a good thing because it forces you to go to that nameplate and gather that information and use that information for these settings. So in this case, if we're looking at how to put a tap setting in, let's say for winding two, it's the tap equals the MVA rating of the transformer times 10 to the third. Okay, that's the total VA, and then divided by the square root of 3 times the high side voltage. Okay, times the CT ratio. So that will give you your tap values, winding one and winding two. So it's a fairly simple calculation. Okay. But the thing of it is you have to go through this exercise if you're using this relay. So when you look at the factory settings, they're both kind of defaulted to tap 5 amp tap. And we know that's not really realistic. You'd never have the same taps on the primary and secondary windings. So we just enter these values that we calculate based on this information from the nameplate. So the other thing I like about the Beckwith too, and I'm not promoting one over the other, I'm just kind of highlighting the differences, is that when you do enable a protective element, you have the ability to just set the output into which output's going to trip if it hits those values. So here we have a minimum pickup of 0.5. Your slope one is 25%, slope two is 60, and then your point break is 3. We have a 20% harmonic restraint set for the relay as well, and an output that it's going to trip to when you go to enter the value. Now let's go to the Schweitzer relay. And of course, these are becoming more and more common in the industry. Schweitzer's done a great job of developing the most modern protective relays you're going to find throughout the industry. But when we look at this right here, again, same identical settings. We're going to put in the MVA rating, how the transformer is connected, the CT ratios, okay, on the primary and the secondary windings. We're going to enable the differential protection. Okay, now this is important. In this particular instance, these values over here are going to automatically configure these tap values for you. Now you can put them in a manual way, but it's really designed to give you what they call the auto tap function. So you'll see here that settings, our slope settings, those are all the same as we put into the Beckwith. Okay, we put in the first slope, the second slope, the slope point break, and then our unrestrained setting. Okay, these are all put in by the engineer. Okay, but these tap settings are pre-configured based on this information, which tells us what? Which tells us that if we put something in wrong over here, our values here are going to be wrong as well. Okay, I'll give you another story. I sent somebody out to do commissioning on a GSU at one of the large utilities in North Carolina. You can only imagine, very large utility. Um, and they went to test the relay, and the relay failed. So the gentleman there turned to the technician and said, "Hey, I thought you said this relay passed on the bench." And he said, "Yeah, it passed just fine. We installed it in the panel and now we're getting ready to commission and it's not passing. What's the difference?" Well, the technician that was doing it on the bench used a particular software program that takes the settings out of the relay, configures the test, runs the test, and then is going to pass the test. The gentleman who was actually testing it for commissioning, once it was installed and ready to energize, took the information from the nameplate of the transformer, configured the test, okay, and they didn't match. Okay, what happened was the engineer actually swapped the CT ratios from the primary and the secondary sides. And if you're just taking the settings out of the relay, okay, it's ultimately going to pass. And if they didn't catch that during the commissioning process, that transformer relay would have obviously nuisance tripped during the energization. Okay, the other thing that we have to be aware of when we're working with the Schweitzer relays is to make sure that you apply the logic to the output contact correctly. And instead of the Beckwith, where you just click a button that says trip output 1, in the Schweitzer, you have to designate your protective elements in terms of your trip equation, and then you have to apply the trip equation to one of the output contacts. Okay, now you can enable a trip equation, but if you don't apply it to the right output contacts, it's never going to trip. So these are the things that are just important to understand the differences between these two relays. Now, each of the relays uses a dual slope setting, and we do a dual slope setting for a number of purposes. Now, back in the electromechanical days, a BDD from GE had a set slope setting. It had either 15, 25%, or I think 60%, and it didn't have the ability to put in a separate slope. Now, the HU from ABB had kind of it had a dual slope characteristic, but it looked like a big swoop. Okay, so the higher up the restraint you got, the higher, okay, the slope looks. So it was a little bit more modern in terms of how it compensated for CT error than the BDD did, but it was a little bit more tricky to test, and it was a lot more tricky to bring into calibration if it was ever out of calibration. But thankfully, with digital relays, we don't have to worry about that. So the slope one is the portion of the graph between the minimum pickup region and what we call the slope to break point. Okay. And because it's a lightly loaded situation for the transformer itself, we don't worry so much about CT saturation or CT error. Okay. But when we start getting higher up that slope, okay, that's used to accommodate transient errors. For example, if it's caused by CT saturation, as the CT saturates, we want to make the 87 less sensitive. Okay, so we include the slope of that element, and it looks kind of like this. This is your restraint region right here, and this is your operate region up here, and then you have your unrestraint where eventually it gets high enough to where we're just going to stop restraining the element altogether. Okay, so it's important to understand that all your modern digital relays are going to have dual slope capability, and this is important in terms of stability of the relay itself, so we don't get nuisance trips if the CTs begin to saturate. Okay, now the other is to make sure that we're applying harmonic restraint or harmonic blocking. Now, traditionally, in a harmonic blocking scheme, if the percentage of second or fourth harmonic was greater than the set pickup, okay, they'd just block the differential. Now, why do we use harmonic restraint? Well, when you energize a transformer, first energize it, okay, it's going to create differential current because it hasn't stabilized yet, right? You're energizing the windings of the transformer. Your current going in is not going to equal the current coming out. So naturally, the differential relay is going to trip. But when you energize a transformer, it also creates these harmonic components, second and fourth harmonics, okay, that we can sense. And if we sense a harmonic a component in the waveform, we can actually block the 87 from nuisance tripping during the energization. But instead of just blocking, they use more of what we call a restraint. And a restraint is important because if you closed in or you energize that transformer and there truly is a fault within the windings of the transformer, you don't want to keep energizing it. So what they do is they use the second and fourth harmonic restraint to actually desensitize, okay, the 87 element just long enough to where it will keep the element from nuisance stripping, but in the event of a serious fault in the transformer, it would actually trip the relay. And here's what a harmonic graph looks like. This is your, say, your normal setting is 20%. So if my waveform has at least 20% of a harmonic component, it's going to restrict the 87 from taking the element, the transformer offline. If it's anything less than that, okay, we're going to trip the 87. So both second and fourth, typically I see just second enabled. If you want to add some more stability to it, you can do both second and fourth harmonic restraint as well. So there's some key issues surrounding new transformers because some of the new materials in our newer transformers have use a high flux density core materials, and that results in lower levels of second harmonic current during energization. So if you have a brand new transformer and you use a typical setting of 20%, you may get a nuisance trip because the core is deeply saturated during inrush, and that can lead to very low harmonic content, which means that you've got to make that harmonic setting a lot lower than 20%. I've seen them go down to 8 or 10% based on the design of the transformer itself. So it's important to understand that. Now, what is the best method to determine how much second and fourth harmonics you're going to see during energization? Well, take an oscillograph when you energize a transformer and get a good oscillograph that will show you exactly what the harmonic component is during the time it gets energized. So there's different methods that the relays used in terms of harmonic restraint. They could do it per phase mode, which it performs inrush restraint individually on each phase, or it can take an averaging. In the averaging mode, the relay first calculates the average second harmonic ratio and then applies the inrush threshold to the calculated average. Then you could do 1 out of 3. In 1 out of 3 mode, all 3 phases are restraint when a blocking condition exists on any one phase. Um, Again, it depends on the type of transformer and how it responds to inrush, and how much stability versus reliability you want in terms of applying those values. So here are some of the common mistakes we see in actually setting a transformer relay, and that is number one, swapping CT ratios between the windings, not accounting for a delta connected CT. If you're replacing an old electromechanical with a digital relay and you have a delta connected CT because you don't want to add another CT to the protection scheme, it's called a delta setting. Okay, and that is just your tap setting on the delta divided by or times the square root of 3. So if you don't account for that, you're going to get a nuisance trip. Swapping the voltages between windings in your configuration. This is a big one. I don't see it happen very often, but back in the early digital days, I do. they'd install the relay and leave the factory settings in there and not change the settings at all, or forget to change the settings. Factory settings are never relevant to the actual operating settings. The wrong transformer configuration. If you don't have that delta Y1 or YD11 set properly, you're going to get nuisance trips. Incorrect MVA rating used to calculate your settings. Um, Not setting the correct second or fourth harmonic restraint values, incorrect mapping of elements to output contacts, not enabling the sequence of events, the SEQ, the oscillography for these elements as well. It's a very, very important thing to make sure you go back and check the settings to make sure your sequence of events recording is being performing properly, as well as your oscillography. So if you're doing a bench test and you create a trip, go back into the oscillography and make sure it coincides with the fault you applied during the testing process. Now, here are some things during testing that'll help you out. Another thing that all digital relays have is a metering screen. And when you first apply values to a differential relay, you're going to apply the tap setting on all three phases for both the primary and the secondary side. That's the calculated tap value, and offset the phase angles between the two sides appropriately. Because you can see we're 180 out minus the 30. There's that DY1 again. So when you meter the relay, the first thing you're going to do when you apply these values, this is kind of a wiring validation, is you're going to look at your metering and make sure, number one, you don't have an element that's tripping, okay, because it should be restraining with these values. You're going to make sure you have all positive sequence values on both sides of the transformer. If you have any negative sequence, that means that you have something wired incorrectly. So two things can happen. It's configured, the relay's not configured the way you apply the test, or the wiring to the relay is incorrect. If you roll a phase, or if you reverse the polarity on any of the phases, on any of the windings, it's going to nuisance trip and it's going to show up in your sequence values. So that's the very first thing that I do when I'm testing a differential. And if you look here, if we roll phase A and B on the secondary windings, okay, you're going to see here right away, okay, that we've got an output contact picking up a nuisance trip. And on that secondary winding, we've got negative sequence values here in our metering screen. Okay. Then we're going to do the minimum pickup. Okay. And we do this one winding at a time. So for tap winding one, we said the minimum pickup was 0.5. Okay. It might be 0.3. Now remember, 0.5, 0.3, whatever is, that's a per unit value. So that is per unit of the actual tap winding. So if I say my tap winding one is 2.187, okay, times 0.5 per unit, that's 1.09 amps. If I ramp this value from 0 to 1.09, that's when the contact should pick up. And we do the same thing with winding 2. For the 87 element, what's important to know is that we have to calculate our values based on the actual tap settings of the relay to find out where the elements picked up. Now, the one thing I like about modern relays is they give you graphical monitoring screens. So you can start off with your tap values and start ramping up either the secondary or the primary side, and you'll see this little cross right here. This will start walking up into the trip zone as soon as it hits that 25% slope line, it's going to pick up. Now, sometimes the differential is calculated differently on the restraint current. Okay, Schweitzer might be a little bit different from GE. Even back the ABB and the HU and the BDD, they calculate the restraint value differently. On one, it's the absolute value of A plus B. In some, it's the highest value of the restraint current. Again, if you're trying to calculate what the values would be between the primary and secondary side to hit this 25% slope, it's kind of a rise over run calculation. Make sure you check with your instruction manual to make sure, but you can always use these visual graphics to check this as well. depending on what the amplitude capabilities of your test set is, you also want to get up past this intercept point to check the slope of the 60% as well. But remember, when you calculate this 25% slope actually starts at the 0, 0 intersection, and it gets cut off right here at your minimum pickup line. Okay, now to validate harmonic restraint is set and working properly, what you're going to do is you're going to superimpose frequencies on all three phases. So take your test leads from winding 2, all three phases, and move them to winding 1. Okay, and while you put the tap value on, or put a trip value on winding 1, let's say this is 2 times the tap value, okay, we're going to double that on winding 1, and the differential is going to pick up, obviously. So then we're going to set our superimposed values to 120 hertz instead of 60 hertz, which is of course a second harmonic, right? And then 20% of 4.372 is 0.874. So we'll ramp these currents up until we hit this value of 8.8874 milliamps, and you'll see that element drop out. Okay, so that's a very good way. Now, you can do that single phase, depending on how it's set, 2 phase, 2 out of 3 phase, or do all 3 phases. But once you see that element drop out at that value, you'll know that that 20% setting is operating correctly. Now, if you're going to do fourth harmonic restraint, we just double this, right? That's going to be 240 hertz. Okay, so this is a nice, tricky little way to check your harmonic restraint. Okay, now here's another element that I want to talk about, because we usually see this set in the Beckwith if it's on a GSU, and it's called overexcitation, or volts per hertz. And what this is actually the ability to have the transformer withstand certain thermal limits, okay, associated with a volts per hertz condition. Okay, so basically what happens is a volts per hertz is a difference between the voltage and the frequency. It's not over voltage, it's not under frequency, it's a relationship of voltage to current. And we see these on GSUs because this phenomena can happen during the excitation. If you have a bad static exciter or an automatic voltage regulator on the generator, it can create a volts per hertz condition that can cause serious damage. And if it's going to damage the transformer, but or the generator, but it can also damage the transformer because they're directly connected to each other. Remember, you have generator, transformer, and then breaker. So whatever happens with the generator is going to happen with the transformers as well. And they're kind of interesting elements. They have to operate at a low frequency because it has to be able to protect the generator as it's coming up to speed. And typically the capability of the generator is less than the GSU in terms of what it can withstand. It could go hand in hand. They could be identical. One could be withstand more than the other. But what's important here is that we make sure we set these properly according to IEEE standards. So overexcitation versus overvoltage. Overvoltage protection reacts to dielectric limits. So if you exceed limits and risk punch, it kind of can punch a hole in the insulation itself. And overvoltage is in a power network that can be caused by lightning strikes on overhead transmission lines, circuit breaker switching operation and faults, and power transformers. They can be exposed to such transient overvoltage during the operation. Overexcitation protection reacts to overfluxing. Okay, so we're talking about overfluxing. Flux, okay, causes heating. Okay, so the voltage excursion may be less than the prohibited dielectric limits or the overvoltage limit. The excess current causes excess heating, which will cumulatively damage the asset. Now, in terms of what thermal limits the transformer itself can actually withstand, well, that was updated. The overexcitation curves were actually developed by GE many, many years ago. and they hadn't been updated in a long time until last year. C-57-107, which was a working group on the Transformers Committee, actually came up with new withstand curves to kind of update that modeling. So in terms of generator protection itself, we see two things. We see under excitation, which is your loss of field protection. Okay, and that's not something that the transformer has to be concerned with. But then over excitation for overexcited currents, and this can the AVR, your automatic voltage regulator, can go haywire and create this situation. So again, this is something that you'll see enabled in a in usually a GSU, but in EHV transmission systems, you may want to see volts per hertz enabled as well. There's certain things that can cause this phenomenon to happen. Things like generator load reduction, power system idling, downstream breaker failure creates a Ferrani effect. Now, most of the times, these events will be voltage excursions. But if you have a voltage excursion while you have a frequency event, it could create a volts per hertz condition as well. So it might be worth looking into in terms of enabling volts per hertz protection in a high voltage system. When capacitors versus reactors, you have one off when it should be on, or vice versa, or runaway LTCs. Again, typically, these are voltage excursions, but if you have a frequency phenomenon going in the opposite direction, could take a volts per hertz out. Now, this is what volts per hertz protection looks like. You have an inverse time characteristic where you have your operating time in minutes and then your percentage of volts per hertz, because volts per hertz is always set in a percentage of voltage divided by frequency, where you have nominal voltage, nominal frequency equals one. Okay. As one starts to get away from the other, you start to have a higher difference of voltage to frequency. So the higher the volts per hertz, okay, the more damage you can occur, or the more sensitive you want it to be. And as you get higher on that scale, your time to where you want to trip um, the element gets longer and gets shorter and shorter. Okay. So, here's a typical example where you have 1.05% might give you an alarm so you can actually take corrective action before it gets too high. Limiter settings can be anywhere from 1.05 to 1.1 per unit. And then, you might want to initiate some tripping in, say, 60 seconds if you get to 1.1. And then for much higher volts per hertz conditions, it'll be much quicker, say in six seconds, or maybe if it goes real high, instantaneously. Again, it's important to check with the withstand capabilities of the transformer itself, and of course the generator. So transformer OEM capability data can be difficult to obtain. I'd refer you to C-57-107 to give you some nominal settings and what that should look like. You have to make sure that you don't set it too sensitive. You apply proper time delays, because if you nuisance trip the volts per hertz element, which can happen very easily if it's not set properly, you could take a whole system down, and I think NERC might get a little bit upset with that. But here's kind of what a transient looks like in the oscillography of it. This is an actual event where we start to have over voltage excursion. We start to get higher currents, but we also see the frequency start to dip, and you'll see right here where your transformer magnetizing current actually comes into play during this trip before it actually comes offline. And this is important to know, because a volts per hertz condition, even if it's not strong enough to trip the element, can create differential current in the transformer itself. So how do we keep a volts per hertz excursion from nuisance tripping during a quick transient? Well, we look at what's called fifth harmonic blocking. Okay, because if you get differential current that has a fifth harmonic component associated with it, they know, okay, that's what that is. It's like inrush coming from the opposite direction. So that's when we use fifth harmonic blocking. Okay, and fifth harmonic blocking is important to enable if you have a volts per hertz element enabled as well. So differential protection, fifth harmonic restraint's been used to prevent undesired tripping, and basically it does the same thing. It will raise the pickup of the differential to desensitize it, because if you do have a fifth harmonic, but you also have at the same time a true fault internal to the transformer, we don't want to completely disable that. So, some common mistakes when we're testing the relay. Okay, changing the setting just for testing purposes. Okay, and I hear a lot of people do that. Well, if I test this element, this one's going to pick up a nuisance trip, so I'm going to disable that element. The problem is they disable it and they forget to re-enable it after they're done testing. So you can get around that by mapping, test out outputs from the relay itself. Changing the logic that would affect the relay's operation and service. And what I mean by logic is if you have a element sensitive to breaker position, but you're not simulating the breaker during the testing process, you may disable the breaker supervision. That's not a good thing. Incorrect wiring of inputs, rolled phases, reverse polarities, assuming the setting relay is valid. Okay, always verify the setting by looking at the nameplate of the transformer to make sure that those values were input properly. Assuming the settings, selecting the appropriate logic for binary inputs and outputs, not validating that the sequence of events record, target indicators, DFR, or testing the relay with factory settings is kind of no-brainer, but I've seen it happen. One other thing that I think is important, we talked about this a little bit, and that is the through fault monitor in the relay. You really want to make sure you enable that through fault monitor, because if you've realized if the relay's seen a number of through faults going through the transformer, when you go out to do maintenance testing of that transformer, you may want to look to make sure that you haven't incurred any mechanical damage, because a through fault actually puts mechanical forces and stress on the windings of the transformer, and over time these through faults can create damage in the transformer, and you may not find out about it until it's too late. So make sure your through fault monitor is enabled as well, and make sure that when your substation maintenance team goes out to test the transformer periodically, they check the relay to see if there's been a history of through faults.